Hello, class. So, what I wanted to go through today was other ways that differential equations and neural networks are being mixed to do physics informed and scientific machine learning. So, in this course, we really went through a deep dive of two different methods, the physics informed neural network and the neural differential equation. And we went through everything about how backpropagation and automatic differentiation works to be able to understand how these methods are trained. But what we're going to be going through today is really just expanding our worldview and just seeing what are the other ways that people are looking into doing, this kind of scientific machine learning. So that way you have a broader worldview of the processes and the methods that people are doing. And hopefully this is like a good introduction if you're interested in looking into at this field for research. So, just to point of note to at the very beginning here, there's the Julia Scientific Machine Learning Organization (SciML), which is all about building um, production quality implementations of these kinds of methods. So, a lot of the examples that we described today have Julia implementations in places like data-driven diffEQ for Koopman operator and Cindy stuff, reservoir computing for these Echostate networks, and a whole suite of packages. Um, and this is the work of I think there's about 40 active people in the development right now, and there's been over 100 contributors over the last 4 years to this space. And so this is a fairly large collaboration that's trying to productionize essentially this full suite of methods as new papers and as new methodologies get developed. There are some other scattered around packages to make note of too. So one to make note of is DeepXE, which is developed by another colleague here at MIT, which is for physics and neural networks. There's PyCindy for doing the sparse identification of dynamical systems I'll be describing later on. And there's other tools in Julia as well, such as ADCME, which is all about physics informed machine learning with applications that are using TensorFlow under the hood for the automatic differentiation. So let's look at some of these alternative methods that have kind of developed through it in the literature and understand how they fit into this greater story of scientific or physics informed learning. And the first one to make note of is the augmented neural ordinary differential equation. So where the augmented neural ordinary differential equation comes into play is that neural ordinary differential equations are actually not a representation of all possible functions. So for example, the Poincare-Bendixson theorem very much highlights this, where it says that if you have a two-dimensional dynamical system defined by an ordinary differential equation, it cannot be a system that exhibits chaotic orbits. And the way that you prove this is you basically say, well, the flow lines of a ordinary differential equation cannot intersect themselves, right? So if you have a given point in phase space, so think about like the Log-Voltaire equation. If you have a value of x and y, then at that value of x and y, there's one direction that the derivative has to be pointing, right? So if you're draw a space of your x and y, then there at each point in x and y there has to be one direction that the arrow is pointing, and you can basically solve the ordinary differential equation by connecting all these arrows and just following the direction of flow lines. Now, what this means though is that we cannot represent all possible functions because think about the function where if you have a circle, now let's say you start in the middle and you want to move to the outside, right? You can't cross the circle, right? Because if you ever hit the circle, then you have to follow the flow lines and go in the circle. And so the Poincare-Bendixson theorem does is it proves that you cannot have chaos in two-dimensional ordinary differential equations because you will either intersect with the circle and thus you will have a periodic orbit, or you will have to go to a steady state. Um, or you start out beyond all circles and you diverge to infinity, right? So these are the total types of dynamics you can have. So you can never have a true chaotic system in 2D. And so what this means though is that there are possible functions which cannot be represented as solutions to ODEs, which means even though the neural network itself is a universal function approximator, the neural ODE is not a universal function approximator. Um, and that means, a few things. Like one is that it means it might be a better representation for learning dynamical systems, right? Because it is constraining to the possible behaviors that can be seen by continuous dynamical systems. But if you do want to use it for a universal approximator, there are ways around this, right? Because the issue is that you cannot go over a flow line, right? You have to be moving in the same direction. But if you had another dimension, right? So if you had this 2D plane, but then you gave yourself a third dimension, and every time you wanted to cross over a line, you go to the third dimension and you go back to this two-dimensional plane, then you could cross over lines. And this is where the idea for the augmented neural ordinary differential equation comes from, which is essentially that if you augment your neural ordinary differential equation with fake dimensions, then you can give it enough room to move around and be once again a universal function approximator. So what you do is you define your neural network as an ordinary differential equation with more dimensions than your actual data, and then you append to your data just some zeros. And if you train the neural ordinary differential equation on this enlarged space, then it is able to be a universal function approximator on the subspace, or that subdimension that your data lives on. And so this gives you a way to be able to use the continuous, the adaptivity, and all these features of ordinary differential equations, but allow you to keep that property of universal function approximation. So this is one way that neural ODEs have kind of been extended in the machine learning literature. Now, when you're looking at scientific machine learning, you generally don't want to do this process just because you want to constrain it to the possible behaviors that you can physically see. And if it's not representable by a physical system, then that is kind of a good property. But this is a method to keep in mind for if you are using the neural ODE for other purposes. This is a very nice technique to be able to make it into a universal approximator when you need to. Now, one thing that we haven't really discussed in this course is that there are many other differential equations. So you have stochastic differential equations and delay differential equations. The stochastic differential equation adds a Brownian motion term, which is injecting randomness into every step. So if you have the differential equation, u prime equals f of u dt. You can also say that this is fraction du dt equals f of upt, or you can move this term over and you have and this other representation of an ODE, right? But this is deterministic. DT is deterministic. And what you can do is you can say, I want continuous noise. I want to add a what's known as the diffusion term, where w of t um, is something that is 0 to it's a normal distribution with mean 0 and variance t. So this is a Brownian motion, right? To understand what a stochastic differential equation moves like, I like to show what's known as the Euler-Maruyama method, which is the Euler method for stochastic differential equations. So what this method is it's use of n plus 1. The next step equals the previous step plus delta t times f of u sub n et. So this is the Euler method, right, that you know from before. And the way that you move to a stochastic differential equation is to append it with square root of delta t, square root of delta t, this eta sub I term, and an application of g of upt. Right, so what's going on here? What is this eta sub I term? Well, this is a term that is eta sub I is it's a standard normal distributed random number. So it's a what you do in practice is you do eta sub I equals rand n, right? And so these standard normal random numbers, to find this eta sub I, you scale them by square root of delta t, and this is what you add to your differential equation. So this gives you a differential equation where randomness is embedded within it. And so this is used to model things like chemical reaction systems. And so you can see here that once again you have a derivative function which can be represented by a neural network, a diffusion function that can be represented by neural networks, and then you can do these more general forms of do recovering dynamical systems, which recovers dynamical systems along with their randomness behaviors. A delay differential equation is a differential equation of the form u prime equals f of u, u of t minus tau um, dt. So what I'm saying here is that you can use previous values of your ordinary differential equation to recover to define the dynamics of your current time. So one way that this is used, for example, is in like biological modeling, where when you are looking at the rate at which DNA is being produced, it's not being produced by the number of transcription factor that's bound to the DNA right now. It's produced by the amount of polymerase that's bound to or the transcription factors that are bound to the DNA at a few hours ago when the transcription started, right? So there's a delay effect that if you remove transcription factors, you do not change the amount of your transcription right now, but you will change it in a few hours, right? And so you can model systems with these inherent delays by using delay differential equations. Right here, you have a function that is, a actual. It can be represented by a neural network itself, and you can do all these same behaviors. In your homework, you went through, for example, looking at, let's pull up the diffie docs here. You looked at using event handling systems to be able to define your adjoint methods, right? So you went to the event handling and callback functions, and you looked at examples like the bouncing ball, where you can define differential equations such that at certain times you hit them with discontinuities. So these are hybrid dynamical systems, and you can, for example, look at define a ordinary differential equation with a bouncing ball, and and you can then train neural networks for finding these dynamics, and so you can have these kind of mixture between continuous and discrete systems, and this is something that's being pursued in many ways. These adjoints can be defined, directly, or they can be done through direct automatic differentiation, and there's many things to explore in the space. And so these are just all different ways of doing, extensions to other dynamical systems, which are being explored. So another work that has been done is the universal differential equation, which is about this idea of embedding physical information into the neural ODE, right? So the neural ODE is all about this problem where you say u prime equals my neural network of u, and so let's try to learn the dynamical system. But in a lot of cases, we know a lot more information about the dynamical system than it's just a dynamical system, right? So one example that comes to mind is, for example, if you have a chemical reaction network. In many cases in biology, you don't necessarily know everything that's going on, but you do know something. There's no reason to start from with no information. Instead, you can start with partial information and recover the rest of the system. Right, so this is the work of the universal differential equation, and what it looks like is you can embed neural networks inside a differential equation. So universal approximators embedded inside a differential equations. It's the what other name to call it than universal differential equations. Um, then with this method, you can say, I don't know how X works, so I define X like by a neural network. I do know how Y works, so Y is linearly related to both Y and X. And you can train systems so that way you learn dynamics in some portions, but you're hard coding physical constraints in other components. And so, you can use one of these neural differential equation libraries to be able to train these neural networks embedded within the system. If you use automatic differentiation, you can treat the neural network efficiently along with these other terms, train the parameters simultaneously or only train subsets. And there's all these different versions that you can look at. You can also, do this with stochastic differential equations, delay differential equations, and basically make use of all of the physical knowledge you have, but only have the neural network cover that last mile for the parts of the system that you are either highly unsure about or the parts of the system that you really just don't know. So this methodology has been shown to be useful in many different cases, such as in climate modeling, that you have a general idea of a lot of the dynamics because they come from computational fluid dynamics, but you know that you only have a partial description from that because you're missing some external forcing behavior, and so you can have the neural networks just kind of cover these other parts of the system. So a universal differential equation is essentially a way to take the neural ordinary differential equation from something that is, not having physical laws or physical information to something that has all the embedded physical information. That way, you're kind of learning. You're purposely learning a non-universal representation of a function, but instead you're learning universal approximators embedded within differential equations in a way that's constrained to give you physically realizable outputs. Another method, which is kind of gained a lot of popularity, is the deep BSDE methods for solving high dimensional partial differential equations. So the idea is that you can use neural networks in a very structured way to be able to solve very high dimensional partial differential equations that might be expensive to solve with physics informed neural networks. So what does that look like? Well, the way that you can think about this problem is that it's solving for a specific class of partial differential equations. It's solving the stochastic control problem. So what it's really doing is it's looking at, for example, the Black-Scholes equation, which is so the way that we think about Black-Scholes equation is that an option is a contract to let you sell a stock at a given value. And so if you have a stock in, at that allows you to sell it a month from now, and it says that you're allowed to sell this stock uh, for $70 1 month from now, but that stock is worth $30, then that contract to sell the stock for 40 more dollars is a contract that is worth $40 in the future, right? Now, if the stock actually cost $90 in the future, but you're allowed to sell it only for $70, then no one's going to care about that contract, right? It's basically worthless, and so that contract itself has a value of $0. Right? The problem of the Black-Scholes equation is to essentially figure out what is to figure out what the contract is worth today, given if you were to have that contract a month from now, that it would have a strike price and it would have a well-defined value. Now, the way that the Black-Scholes equation works is you define that the way that your stock prices are changing is via a linear stochastic differential equation. Right? So one of these differential equations with randomness, but it's just the extension of the linear ordinary differential equation to the linear stochastic differential equation case, where you say, I have exponential growth in stocks, but the amount of randomness is proportional to the current amount of the stock. Right? That's essentially what this linear stochastic differential equation is saying. But but you can think about doing something like a nonlinear Black-Scholes equation. So you can say, now I have a whole scientific model for how stock prices are evolving. That includes, depressions and recessions and irrational behaviors and all these other types of behaviors. How can I solve the Black-Scholes equation? And the traditional way for solving it doesn't necessarily work anymore. But what you can do though is you can say, if I was to have a given chosen value of my of my contract price right now, and I know the stock prices, I can solve forward this differential equation for what these stock prices will be in the future, and then I can solve backwards what given the stock prices I know what the contract price should have been given the stock prices back then, right? Like if you know that the stocks have increased in value a whole bunch, then you know that your contract will have a lower probability of actually having value in the future. So you'd lower the price of the contractor. You'd lower the valuation of the contract. 2 weeks from now, if the stocks are really high priced at $150 2 weeks before the strike time. Right. Whereas if the stocks are tanking and you still have the ability to sell it 2 weeks from now for $70, then your contract is probably worth a lot. And so what you can do is you can solve forwards in time this stochastic differential equation, and you can solve backwards in time this what's known as a backwards stochastic differential equation. And the backwards stochastic differential equation will give you the valuation of it will give you the valuation of the option. Now, what is the actual differential equation that you should be solving backwards for? Not the stock price, but they should be solving backwards for the options price. This is something that is very hard to define in theory when you have when you have a nonlinear dynamical system or a nonlinear function that is defining your stock price growth, right? But there is something you can do there, right? Because you can say, I know that I have, so I can represent what the dynamical systems of my backwards process is by a neural network. And I will know that I have found the correct neural network because um, I need to have two things be satisfied. I know the terminal condition, right? So if the stock price was if the stock prices are T in the future, and I am if the stock prices are T in the future, then my initial condition for what the value of the contract is, I can know, right? So if the stock price is $30 in the future, and I could sell it for $70, then my initial condition for the terminal time point for the contract's value is $40, right? So you can have this terminal condition, which tells you how to do initial conditions for your um, for the contract. And then what you know is that you should be able to pull this value back, and you can define a then you can find if you know what value it hits, then you can know what value after you pull it back, you can know what the valuation should have been at the previous time, because you know that in the future for that run it would have been worth $40, right? And so then you can train a neural network to be able to satisfy and say, okay, now I should be able to solve this dynamical system forwards, right? Where I guess a contract. I have a neural network guess at my current time 1 month from the stock chain, from the strike time. Should have a neural network guess what the current value, today's valuation of that contract is. I have a neural network that defines how to be changing the valuation of the contract price as I am evolving my stocks. And then at the final time point, I will know whether these neural networks got the right answer, because they should, the valuation of my contract at the very end of the system should be given by the difference between the strike price and the current valuation, the difference between the strike price and the current value of the stocks, right? So this lets you then define only a forward pass, right? So you define a forward pass, that is, take the initial condition for the contract from the neural network, solve the different dynamical system for the contract and the stochastic differential equation together for the where the dynamical system of the contract is defined by a neural network. And at the very end, you should have that the valuation of your stock price, or the valuation of your contract, should be equal to the difference between the strike price and the stochastic differential equation that defines the stock price in the end. Right? And now, what if that isn't true? Like, what if that difference isn't true? Well, that means that the neural networks that you have defining your dynamical system and your initial value for the contract price are incorrect, right? So that gives you a cost function where you say, here's what I know needs to be correct after I run a forward pass. Find the parameters of my differential equation, or find the parameters of my neural network, such that this valuation process ends up giving me something that's always a true valuation. And this is the deep Bsde method. So basically, what it lets you do is these extended semi-linear partial differential equations that represent things like nonlinear black Scholes. You can solve these kinds of problems by essentially saying I can represent this partial differential equation as this backward stochastic differential equation, where I don't know what these terms are that would represent parts of the dynamical system. But I can represent these parts of the dynamical system and the initial valuation of my contract as neural networks. And then I can write down essentially a recurrent neural network, which is actually equivalent to the Euler-Maruyama discretization of the stochastic differential equation. And then you can train these neural networks embedded within these stochastic differential equations to be able, by knowing that the terminating condition needs to be satisfied. So that gives you the cost function. And so what this lets you do is this gives you a way of solving 100-dimensional stochastic differential equations, and then by training these neural networks in stochastic differential equations, you get a solution to 100-dimensional partial differential equations. And if you look at the implementation, such as in neuralpde.jl, this is something where in like a few minutes, you can solve 100-dimensional partial differential equations with just a few lines of code. Now, this is pretty tremendous, right? Because if you think about, let's say I was to have like dx or delta x for a finite difference method for a partial differential equation, and let's say I had 10 data points in 100 dimensions, right? What would that grid size be? Right, so how many points would it take to do a finite difference method where you only have 10 points in 100 dimensions? Right? Well, it would be 10 to the 100 points that would be required. And so let's actually just use, Wolfram Alpha to figure out how difficult this problem is in with a standard finite difference method. So it would take 10 to the 10 it would take 10 to the 10 numbers to represent just the spatial grid of the for the partial differential equation, and then it would take 64 bits per number, right? So how many bits would this actually take to represent? Um, and now let's represent this as gigabytes, right? How many gigabytes of RAM would you need to be able to solve a finite difference method for that partial differential equation? And you would need about 10 to the 92 gigabytes, or let's do this as terabytes. You would need 10 to the 89 terabytes of RAM to be able to hold one time point of that solution in memory. So finite difference methods are completely untenable for solving this kind of partial differential equation. But if you represent it as, so finding a neural network for a stochastic differential equation that relates back to the partial differential equation, then once you've trained these neural networks, the neural network that tells you the initial contract price is the thing that tells you, well, what the initial contract price should be, and that's the solution to the partial differential equation. And so this gives you like an asymptotically much faster way of solving this partial differential equation than classical methods. And a lot of research is going on to really try to figure out if there's more ways to use these kinds of methods. One point to note is that you can represent this deep Bsde method as a universal stochastic differential equation, which then lets you understand how to do, not the recurrent neural network version, but also the what is the implicit version, what is the version that allows for stiffness in the dynamics of the stock market, what is the version that allows for adaptivity of the solve. And all these issues have been worked out by treating it as a universal stochastic differential equation. So this is a very interesting method which has which has applications to, for example, nonlinear black Scholes. So if you have a very sophisticated representation of the market, right? Then you can say how should I be evaluating these options contracts? And you can get methods which don't require the linearity assumptions of the traditional Black-Scholes methods. Um, the other type of problems that are solved by this method are stochastic optimal control problems. The stochastic optimal control problem is a problem where you say, I have a stochastic dynamical system that is that is doing the evolving of my general dynamics, but then I allow myself to have a control process. So let's call it C of t. And what you can do is you can say, I want U of t to I want U of t to do something, right? So, for example, I can tune around C of t as much as I want. So, like for example, this is the amount of electricity that I'm putting into the motor for motors 1, 2, 3, and 4, right? And I want U of t to be, U of t is the current position of my RC car. And I want to make sure that, and I want to find out how to be changing these electrical currents such that the RC car moves along a course, right? For example. So what I do want to do is I want to find, given the course that I want it to follow, I want to find what the control variable should be. And so you have a loss function. So for example, you have a loss function that says, I want to have U of t at each time point. I want this to follow my course. Then your loss function can also say, each time that if I'm just running the motor as high as possible, then I'm using too much energy. So I might want to have a loss function also minimize the total energy at every single time point, right? So if I add up the energy that of the controls and I want to minimize this, all right, instead of doing this at discrete time points, I might want to do this as the integral over all time points, right? So when we did adjoint methods, we looked at how you would actually take the derivative of with respect to the ODE solution over an integral of all time points, right? And this is where this comes into play. So here, what I'm also saying is that I don't just have an ordinary differential equation defining, you defining deterministic dynamics. I also have a ordinary. I'll have a stochastic differential equation, which so there's stuff like wind that is jostling the RC car around, and I want to figure out what is the right way to do this control such that on average I have the lowest cost. So I can say on average I have the expected value of my cost is minimized. And this is the stochastic optimal control problem. And it turns out that the solution um, for what is C of t, you know, um, you can solve this directly. So you can represent C of t by a neural network, and then you can find C of t. Right. Once you represent C of t as a neural network, you actually have a universal ordinary differential equation, and so or universal stochastic differential equation. So if you look at, for example, the diffie-q flux documentation, you can find examples in here like solving optimal control problems, where you can solve this optimal control problem by representing these control values as neural networks and then training them directly in the dynamical system, right? So this method is treating it as a universal differential equation. But you can also think about it as a partial differential equation. So you can directly write down that the the solution to the stochastic optimal control problem is given by the Hamilton Jacobi Bellman equation, the HJB, which is a partial differential equation that satisfies exactly what's described in this deep Bsde method. You can actually think about nonlinear black Scholes as a form of stochastic nonlinear control. And so what you can do then is you can solve these stochastic nonlinear control problems by writing down the partial differential equation that's associated with that control problem, and then directly solving that partial differential equation by using the DPSD method. So for example, the classic linear quadratic control problem is to minimize a cost function where you put a mean squared error on the control's usage, but then you also allow yourself to have a state that you're trying to hit, right? So this is exactly this case where you say, I want to move on the course, but I have mean squared error at every single time point for actually using my controls because there's a cost of the electricity. And so if you want to minimize this cost function, you can write down a Hamilton Jacobi Bellman equation for that, which follows this form. It turns out to be one of the forms that falls into this more general partial differential equation. And so you can use this DPSD method to directly discover the solution to the stochastic optimal control problem. So this means that the DPSD method, it's useful in finance, is useful in control theory, and there's a lot of other applications that can be found. And the interesting thing is that you can represent this you can represent the solving of this DPSD method via a universal stochastic differential equation, and so then you can use adaptive methods and everything for solving this. And this is what's done in the neural PDE library, where you can div neuralpde.sciml.ai, and you can see that using the solving these Kolmogorov equations or things that follow 100-dimensional Hamilton Jacobi Bellman equations is just a very quick few lines of code these days, which is training neural networks embedded in differential equation solves. So this is one area where scientific machine learning has really exceeded classical methods in a way that by using the high-dimensional cursive dimensionality behavior of neural networks. Another type of method that you can look into is connections to reservoir computing. So what reservoir computing is trying to solve is the fact that full neural networks are really hard to train against some kind of dynamics. So one kind of dynamical system that is exceptionally hard is uh, is chaotic differential equation. So the reason is because chaotic differential equations have a divergence in their tangent space. Actually, the rate of divergence in the tangent space is the Lyapunov coefficient. And this gives you a problem with traditional methods because the tangent space, right, is where we represent the dual numbers for the for monotomic differentiation, or the tangent space is also a representation is related to the representation of the pullback values that are done in the adjoint methods. And what this means is that if you have a chaotic dynamical system, these derivative terms are diverging exponentially. And so, if you try to just use reverse monotomic differentiation on something like the Lorentz equation, you actually will find that you'll get infinite derivatives if you take it out far enough. So that's not good, right? It's pretty hard to train a neural network if your neural network is giving you infinite derivatives. Like your parameters would go to infinity, and you just can't train it. So chaotic systems really pose a problem for scientific machine learning. Another difficult type of problem are stiff differential equations, because there's actually a really good paper by Paradikis' lab, which is the gradient pathologies, understanding and mitigating the gradient pathologies in physics-informed neural networks. Or what they show is that if you have stiffness inside of your differential equation and you're trying to learn it with a physics-informed neural network, then what happens is your gradients actually grow to a whole nother order of magnitude. And what that means is that you have large eigenvalues inside of your Hessian, and that means that you have a very ill-conditioned optimization problem. It ends up being a very difficult optimization problem to solve. And so what this means is that when you have stiff systems, you tend to have very difficult optimization problems. And that's not good because a lot of scientific models are very stiff, right? So how can you kind of get around these issues? So one way that's being investigated is something called shadow adjoints. I'm not going to be going into what shadow adjoints do, but essentially it's a renormalization technique. So that way you don't get the solution to the exact derivative, but you get the average of the derivative over all time, which, if your system is ergodic, is the average of the differential equation or of the derivative over all initial conditions if you're looking at the derivative on the attractor. So this is very much only for ergodic dynamical systems, but it gives you a well-defined derivative in some average probabilistic sense for these chaotic dynamical systems, which no longer tend to have deterministic behavior because of their exponential divergence in values that start nearby. So there are methods that try to do more advanced adjoints for handling these kinds of differential equations, but one of the methods that have done really well on these types of problems are completely different, and they're called echostate networks. So here, for example, is a representation of an echostate network where what you do is you fix the matrix WFB and you fix the matrix W here. So you take random matrices for WFB and W, and this is what you call the reservoir state. And then you have what's known as the output state, which is a projection of the reservoir state. So G can be any possible function, and a lot of people actually fix G to be the identity function, but it can actually be any function that's invertible. But let's think about it as the identity, right? Um, so what this does is it without defining without this W out in here, this defines essentially a random differential equation, or this random dynamical system that is just doing things, right? And you can make it a very high dimensional system that is just doing things. And the problem then is to find a projection, which is W out, that goes from this high dimensional random reservoir to the actual output state that you want to observe, right? So you want to make y sub n be the thing that matches the time series you're trying to match. Um, and because you fixed the behavior of the reservoir, you can actually turn this into a problem of doing a least squares fit to find out what W out is. And this is the echostate network, where now you don't need to do backpropagation, you don't need to do adjoints or anything, because now training an echostate network, this training process is actually just finding W out, and just finding W out is a least squares regression that can be done, for example, by QR or SVD factorizations. And so this is actually a method that's been shown to be able to produce the and learn the behavior of chaotic attractors. So here, for example, is what's going on when it tries to learn the Lorentz equation. Even though you are going to have exponential divergence in your predictions, it's still going to learn behavior that fits on the same chaotic attractor. So it's able to kind of learn that average behavior that you'd have to use something like these shadow adjoints to really otherwise be able to predict. Now, another way that this is being used is for improving the ability to predict on stiff systems, right? Because this is another type of system that have gradient pathologies and is hard to train with traditional ways of doing adjoints and gradient based optimization. So one way that has been investigated to do this is with a continuous time echostate network. So instead of having a discrete time reservoir, what you can do is you can change this formulation such that you have a random differential equation that is defined that gives a continuous reservoir. And then instead of using time points that are uniformly spaced to be able to do this prediction and train your W out, you can try to learn stiff differential equations by using the adaptive behavior of a stiff differential equation solver to give you more time points at the more difficult portions of the equation, and then make it so that way you have a easier time fitting the W out matrix. And so this has been shown, for example, on here's a problem called the Robertson equation, which is a very classic stiff differential equation, where you can showcase that a physics-informed neural network trying to learn this behavior, it does not do very well because of the gradient pathologies in the training process. So it's trying to predict this blue line that is kind of underneath the green one. So it's trying to predict this blue line, but it does not do a very good job at doing so because it is not having a good time with these gradient pathologies. And so it's not able to actually get to a very good minimum because of the stiffness in the data and the stiffness in the dynamical system is trying to train against. For the discrete time echo state network, the first point is here, but this is actually log scaled in time, and where it's doing a step where it has 100 time points in space. And so it's trying to predict all the way up to 10 to the fifth. The first time point is going to be at t equals 100, and so it's having a really difficult time trying to recover the information that's happening in this really quick drop that's happening in log time. In fact, the first time point for the uniform, 100 delta equals 100 is actually beyond the entirety of this whole dynamical spike. And so, if you look at it in log space, the traditional discrete time echo state network completely misses the dynamics of the second species of this ordinary differential equation. But you can alleviate these issues by, you can get your time points from the adaptive stiff OD solver. So just using 60 time points in time, so less time points than the discrete echo state network. You can actually have a continuous time echo state network that matches the behavior of this very stiff system almost perfectly. And what this means is that this gives you a way to be able to handle these very high and train surrogates of these very high dimensional very stiff systems without having to do gradient based optimization, which can be very unstable. And this gives you a way to, more stably predict the behaviors of these stiff differential equations. So this is still very early on in the research, but it's showing a lot of promise for handling, these very stiff systems where, neural differential equations and physics-informed neural networks tend to fail. So this is another kind of it's a completely different way of thinking about training systems and scientific machine learning, but it really gives you it really moves around and gets around the issues that physics informed neural networks and neural ordinary differential equations tend to have on systems that are very much prevalent in the scientific machine learning literature. Now, another type of algorithm that people have been looking at is automated equation discovery. So, this is the question of if I have a bunch of data, can I actually just to completely discover the symbolic equations that describe the dynamical system that generated the data process? And this is one well-known algorithm for this is the SINDI algorithm. So, sparse identification of dynamical systems, or SINDI. And the way that this method works is you take all of your data points in time And so let's say you have this whole matrix of data points and you evaluate them in a basis, right? So you can evaluate them in a basis like let's do the square of all my data points, do the cube of all my data points, let's do the sine of all my points, the cosine. And once you evaluate this basis, you can put them all in a big matrix. And then you can also have a big matrix of all of your of all of the derivatives. So you do need to have a derivative estimate of your data, which I'll mention in a second. And then what you can do is you can try to solve, here I have a matrix of my derivatives. Here I have a matrix of all my terms inside of the basis of inside of the this basis of possible functions. Now let's do a sparse regression to find out what the coefficients are on this basis that define the dynamical system. That would be, f of basically you would define the system, so that would be like, for example, if the basis says there's only a 1 in front of the sine term and a 0 everywhere else, that would mean that sine of x is x prime equals sine of x, right? So once you solve the sparse regression problem, then it gives you for the coefficients for the values that are multiplied to this symbolic basis, and then you now have a symbolic representation of this dynamical system. So all you have to do then is do a L1 regularized linear solve, which is done by methods like lasso, and this is the Cindy method, right? So if you look at, for example, data-driven diffie-q, if you look at, for example, data-driven diffie-q, you can go to the package and you'll actually see these examples where it takes in data from the Lorentz equation. It says this is the basis of functions I'm going to allow. Now perform simplification on my dynamic systems and print out the equations. And then it says your discovered system is this, and you can actually print that out directly to LaTeX. So I mean, this is really a from data to law tech kind of version of scientific machine learning. Um, Let me find where those notes are again. Yeah. So there's some packages building up, which is all about how do you do this symbolic regression type of technique. Now there's a bunch of caveats to explain here. So for example, the way that I explain the method, it requires having derivative data, and so what you can do to get derivative data is you can, for example, do a cubic spline. So let's say you can look at a library like data interpolations.jl, um, and so you'd say, well, what if I had a bunch of data in a time series, right? What you can do is you can fit a spline between your data points, and then you can take the derivative of the spline. That kind of gives you an approximation to what the derivative is, and then you can do signification against that derivative. But notice that if you have very sparse data, then doing that interpolation might not be very informative, or it might not be very correct with the derivative estimates, right? So what's shown in the universal differential equations paper is that you can define a differential equation with neural networks embedded in it, right? So you can define a neural network or a differential equation with neural networks embedded in it. Then, if you want to discover what the dynamical system is that this neural network is satisfying, right? Then what you can do is you can take input-output pairs, right? So you can put x, y's into the neural network to be able to get outputs of the neural network. And that is then a method that gives you a way to be able to fit the dynamical system and then get estimates essentially for what the dynamical system's output is. And then you can perform the syndication directly on the neural network to be able to recover what the neural network is in symbolic equations. Um, and then you can also do this, for example, if you use the universal differential equation, you can embed prior knowledge about your differential equation. So that way you're only learning smaller equations. And so this is actually shown in the universal differential equation work. Um, where, for example, here is a system that is recovered. So this Log-Voltaire equation is a system that is recovered with this information where it has prior knowledge about parts of the Log-Voltaire equations, but then it uses this data to discover the symbolic equations for what the missing terms of the dynamical system are. So it discovers all the quadratic terms, then it's able to extrapolate forward in time correctly because it's learned the complete dynamical system from just a little bit of data on what the drop is. So this gives you a really nice way to be able to, learn differential equations and get them into symbolic mechanistic hypotheses um, in a way that is incorporating all of the prior knowledge that you have about the system because you're predefining all the physical laws that you know. Other ways are being investigated to incorporate deep learning into this process as well. And so there's a really nice paper which says, you don't need to be learning in the original function basis. You can be learning in the Koopman operator basis. Um, and then you can represent the Koopman operators via these neural networks. And then, this might be an easier way to do syndication with less data. So this is one way that you can do it. Or another aspect of the research that is really being investigated is how to improve the efficiency of the symbolic regression methods. Um, so, for example, there's like PI-SIND, which is handling these more difficult problems using a implicit version of the dynamical systems. So, essentially, a differential algebraic equation, and it's a more robust method for doing this sparsification. So that is all about sparse regression, and there's a lot of work going on in this area for how to mix neural networks and sparse regressions to be able to directly recover, the mechanistic laws that define the dynamical system instead of just having a neural network representation for it. So last but not least, there's surrogate acceleration methods. So surrogate acceleration methods are kind of odd, right? It's basically like if you spend enough time training a neural network, you can sometimes represent the solutions to your differential equation via a neural network, where the neural network is cheaper to evaluate. Um, and so this gives you a lot of nice headlines, right? Which is like, there's this paper which claims to have, done it would solve these three body equations 100 million times faster. But if you actually dig into the details, you do get a 100 million times acceleration, but it took 10 days to be able to generate the training data set to train the neural network on. Right. So is that actually faster? Well, it's not faster if you need to solve the problem once, but if you do need to solve the problem hundreds of thousands of times, then taking the time up front to train the neural network to be what's known as a surrogate, right? So something that reproduces the behavior without actually being the original system. These surrogate techniques can be a nice way to accelerate. Another case where they really show up for acceleration is more so for changing the time point in which um, the compute is done. So one example of this that we're actually looking at in the Julia lab is in power systems dynamics. So for example, if you want to control a power grid, so this is something that's becoming very relevant because of the duck curve. So if you don't know about the duck curve, this is a curve that says that the amount of power that is required during the day is so the total load on the system, um, the amount of power that people are using during the day, it actually has a decrease because you're increasing the amount of solar load that you're putting on. So people during the day are now generating a lot of solar power, and what this means is that you have this duck-looking curve where you need to, as a power plant operator, you need to be putting less power into the power grid when you see that more solar inputs are coming in. Otherwise, you'll overload the grid and you can short circuit the whole power system. Right, so this is where the whole idea of smart grids is coming in because as new renewable energies are adding new sources, you no longer have one power plant supplying all the energy, and so you need a distributed smart way to be able to, control the system. And so you have people trying to solve partial differential equations on the fly, be able to tell you how you should be changing the operation of the power grid. But solving a partial differential equation is extremely expensive, right? So if it takes 10 days to be able to solve the partial differential equation, it's not very useful when you need to make a decision in a few minutes. And so what you can do though is you can try to train a surrogate that is, you spend like a year of compute time to be able to build a surrogate of the partial differential equation solution, and then once you have a neural network that takes in the parameters of the differential equation and directly spits out the solution, then you can have a very fast surrogate that you evaluate on the actual power grid to be able to do this control, even though the partial differential equation that is defining the underlying system you're modeling is too expensive to do in real time. right? So you basically spend a year of compute to come up with a neural network that gives you real-time solutions to a very expensive process. So one of the ways that surrogates are really being used is in this amortization, where you're spending a lot of pre-compute time to then be able to do things in real time. So you do a lot of pre-compute time to learn the way that you should be doing a stochastic optimal control problem on a drone, so that way when you ship the drone, you only ship the pre-trained neural network and you don't need to do this solving process on the fly. So these surrogate dynamics are probably one of the most common ways that people are looking into scientific machine learning, because it's very easy to find a way to be able to train a neural network to make a system faster. Though you do have to really make sure that you take into account training time. If you're not, or if you're, you have to either do one of two things. You either have to be designing the way you're using the surrogate such that you don't need to worry about training time, right? So, like, if you care about real time solutions, then you can pre-train to be able to get a real time solver. And if you don't care about the way what happens to pre-training time, it might take a whole lot longer to be able to train the surrogate, but that might not matter for what you're doing, right? So you either need to figure out the right way to use your surrogate to be able to solve your problem effectively, or you need to come up with cheaper to train surrogates, or surrogates that train on the fly. So this is done in something called like surrogate optimization. So surrogate optimization, where these are these types of methods that train circuits on the fly to be able to then perform optimization faster by querying points from the surrogate instead of having to do more solutions from the differential equation or whatever program you're trying to optimize. So this is a nice survey of the many of the different ways that scientific machine learning is being used, from accelerating systems to giving symbolic equations out for systems to handling stiff and chaotic systems, and solving high dimensional partial differential equations, and um, and training neural networks in a way that is incorporating past known physical laws, or by allowing handling of many of these different dynamical systems. So this is a whole kind of field that has really evolved, and hopefully this course gives you a good overview of what are the methods that are being able to use, or what are the methods that are being used to train the basic physics of our neural network and neural ordinary differential equation. And then you can probably see how you can move beyond that by defining adjoints of stochastic differential equations, embedding prior knowledge, and doing all of these techniques either in conjunction with neural ordinary differential equations and physics conform neural networks, or as methods to kind of go beyond what those previous methods could do. So I hope you enjoyed the course. I hope you find this whole area interesting. And if you want to do research, or just continue or dig in more into these materials, please feel free to contact me at any time. This is a research project that's going on. It's also a software development project, right? Because the SciML organization has sorry, the SciML organization is a whole organization that is all devoted to high performance implementation of these methods, so high performance and parallel implementation, which directly goes with everything you've learned in the course. And so there's 100 repositories which are going around and you know becoming like standard implementations of these scientific machine learning techniques. So if you're interested in the implementation and the use of scientific machine learning techniques, feel free to contact me or explore these tools more. Or if you're interested in the methodologies, once again, feel free to contact me and talk about potential research projects, because this is a live space. There's a lot that's going on, and there's a lot to be done in the near future in this field. So thank you very much. I hope you've enjoyed this course, and I hope that this course is useful for you in your immediate future, or even if it's not useful. I hope you had a good time just learning how to, build high performance codes, and how to integrate neural networks and machine learning into what you're already doing with scientific computing and all of these differential equation solves and everything about scientific modeling. So thank you very much.